or the second question.
Where is parallelism found in modern computers?
Okay, so that's the first question, just where do we find parallelism? There's different types of people in this class. We have some that are majoring that might be programming. There's some that are majoring that might be more in infrastructure. There's some of you that are minoring in either computing area or computational science, and you're just more interested in using parallelism for your research purposes and trying to understand that. And so one of the key ideas is that parallelism is found in a number of different places in computer architectures. And so the first thing we're going to do is say, where is it found? And so where can you take advantage of parallelism? So that's kind of the first question that we're addressing. We'll address it in foundations. We'll use some of that later in the course. It's another question in foundations we're going to be addressing.
What architecture?
Okay, so what are some different architectures, parallel architectures are available to us that you might use? And again, it goes both ways. You might be the one developing that architecture and using it, or you might be one developing it, or you might be one using the architecture and want to be able to make a good decision. And do you want to use that architecture or not? And then the third question.
Why?
It's a good question, but not the one I'm thinking of. So you're thinking, where is parallelism, what architectures are available, and what programming models are available. So now you're looking at the software. So really, you're really focusing on where do we find parallelism, what's the hardware available to do parallel stuff, and what is the software that's available to do parallel stuff. Okay? Those are really what we're focusing on. And so those are the questions we're addressing in the foundations piece, which is the first part of the class. Second part of the class after the first month is going to be what? What are we going to do in part 2 of the class? We're going to build our own clusters. Yep, and we're going to use Raspberry Pis. The first time I taught this class this way 2 years ago, I had you buy your own. It itself was kind of a cluster because everyone would buy some different kinds of it. And so what we decided to do is I've got 10 on their way, and we'll be into our own groups, and they'll be exactly the same ones, a lot of them preloaded, so it's going to be a lot easier to build the clusters and to learn from them. In building the clusters, I think it'll be nice. You're going to learn some other things. You'll be using command line interfaces, so that'll be something new for many of you. You'll be working in a Linux environment, so not only maybe have you used Windows as an operating system and the OS X as an operating system, now you'll use a variation of Unix, which is called Linux, which is nice just to see one. And what you will discover probably is that, at least at the ways we use it, they're really pretty much the same. You just have the same kind of interface. You get to the same type of thing. So there's not a lot of differences other than oftentimes your graphical user interface that you see. So we'll be doing that. So that's the second part of the course, is building your own cluster. You'll be working with Linux. You'll be doing some command line interface and processing and getting things set up. And again, I'll have that available. We'll be set up with 5 different lab stations back there, so there'll be more of a lab environment, basically. You'll be working with some individuals in your group. And then the third part is, of the course, after we build the clusters.
Presentation.
Not quite yet. But you will be doing a project. What are we going to do with the clusters? Just build them? We're going to program them. So we're just going to look at some different parallel programming techniques so that we can look at some different of the tools and libraries that are available that let us do the parallel processing. So that's kind of the software side. And again, there's a book that we'll be using. It's just a small one. It just talks about Raspberry Pi, but this book itself has an overview of the entire, a quick overview of parallel processing. It talks about how to build your Pi clusters, and it also talks about how to program. So out there on Blackboard, you will see that there are a lot of resources available. I got 5 copies of this, and they downloaded the PDF version. So you can go out there and actually look at this book. I ask you not to copy it. I ask you not to print it, because that would be violating the copyright law. But we do have 5 versions available that we can use in our 5 labs. So you can feel free to go out and just take a look at it and be reading through it as a student. I don't really have a count as if 5 of you are going to do it all at once. I doubt you would all at once be looking at it together. So hopefully we'll be good there. So that'll be out there and available to you. So for those of you that were gone last week, that's pretty much a quick overview of the course. Our outcomes are really to focus on what are the, where is parallelism found for us? And then secondly, what are some of the hardware architectures available to us? Thirdly, what are some of the software programming capabilities available to us when it comes to parallel processing? In the course, we're going to do foundations just to make sure we all have some pretty solid base that we can come back to. And to get our hands dirty a little and actually do some building a small cluster with Raspberry Pis, and then we'll do a little programming. The last piece of this class now, Logan, is
Presentation.
project. Okay, so each one of you are going to be doing a separate project. The project itself can vary greatly from an actual topic. So some of you who are maybe here for computational science perspectives or math or what have you might want to find a topic related to that, some more application, and it can be actually research where you're digging into it. Or it could be actually a tool to decide you want to try to find a tool where you might have access to, say, a cluster somewhere on the internet, and you want to learn how to be able to use that for your research so you could dig into that, so it'd be much more practical. On the other side, where some of you, I know some have already talked to me, I know Ashby talked to me about a very specific use and application of one when it comes to like cryptography, which is good because one of the threads that we like to look at are cybersecurity. So if your topic can be connected to cybersecurity or even ethics in some way, it's always nice. So he's actually doing a programming project, but you don't have to. You can do more of a research, so that would be up to you. So the bottom line is we'll have, there's 15 of you in here, so 15 different projects that eventually we'll hear about in presentations, which will be kind of interesting just to learn more about probably the more applicable use of parallelism. Okay, so that's the last piece of the course. All right. So in the foundations, there's going to be 4 parts to the foundation. We're going to do that over the next 3 weeks or so. And the first one was just really getting into the concepts and terminology. So that's where we are right now. And so what we're going to do is we started it really on Friday. We went through, you're basically building your own textbook. And so what I want you to do is make sure you get a little binder, like hold yours up. There's an example of one. And in the binder, you'll have some sections in there. One of them, there you go. And the first one will be basically on foundations. And so I'm going to be giving you handouts, like I already gave you a series of handouts already. You'll be filling in some notes. You'll be taking some additional notes. And then you'll just be putting those into your binder, which basically creates your own textbook. And then as we go along, you'll have some more notes from me. You'll be putting some information there from when you build your cluster, from when you program your cluster, and from your project. So that all together is just kind of a collection of what you're going to be pulling from this course and maybe be able to go back and reference if we ever need to as you're using parallel architectures. Okay? So what I thought we'd do again is we'll just go over what we discussed. We as in you can tell me, those of you that were here last week, and you can tell those that weren't here last week, without using your notes. So if you kind of give, let's just look at mine. And for those of you that haven't, you can fill yours in a little more and just see what it is that were some of the key points when it came to concepts and terminology and what we were discussing. So, given that. Did you hear that beep? Oh, yeah, there it is.
Not have this.
What's that?
Does anyone not have this?
Did you get an extra one?
Yeah.
Oh,
I
I probably made a few extra copies. I think, I don't know if Zach has one.
No.
Okay. Like I said, I put this together, so you'll see the spring of 2016 a lot on these, because that's when I initially put it together 2 years ago. All right. So first thing I did was introduce just some of the sources that I've used to put this together. One of the key sources is this Introduction to Parallel Computing. It's from the Livermore National Laboratory. And there's actually a link to it there that you can go out there. This is actually the first tutorial out of several for someone who wants to be looking at using their cluster systems that are available from them. But I thought it was a nice one because it had just a lot of information along those lines of those 3 questions. So it's starting off with what is parallel computing, where do you find it, why, and then it gets into the architectures and it gets into the programming. So it's a nice thing to follow. I already talked about the book that we have, the Raspberry Pi Supercluster. There's a few books. This course, as I mentioned last week, has evolved from a couple other classes. One of the classes has been like an architecture class, and one was an operating systems class. And it used to be 2 separate classes. They merged into one class, and now they've kind of evolved into more focus on the parallel architectures and programming. And so anyhow, as I go back and talk about some of this, I've been pulling from books in the past. This one's really old, but it's just giving me the fundamentals of some pipelining concepts that I've used before. And then you see a few other ones, especially this one, gets into more of designing for performance. So We'll get into this one a lot when we actually talk about the hardware side. We'll be using that. So anyhow, just some of the sources that we're going to be using and that I pulled from. Some of these are actually out there on Blackboard that you can dig into. So like this is on Blackboard. As I said, this is on Blackboard. The chapter that I use from this is on Blackboard. So there are some of those available if you want to reuse those as references. Okay. First thing here, so those of you here last week, what was the key idea in this whole slide for those that weren't here last week? Go ahead.
So where do you find parallelism? Start from where there's non-parallelism?
Okay. So in order to understand where we find parallelism, we started from where is there not parallelism. So basically a sequential machine. And we're using this concept of the von Neumann architecture, which is something that is a very common architecture. And so in this picture here of the von Neumann architecture, there is not any parallelism. Everything is done sequentially. Your instructions are executed one after the other, and they have to be fully executed before the next instruction can even start. And if I have to get data, I can only get data sequentially. Okay? And so as we look at these pieces, and as other people who may not have seen them write these pieces down, what were these important pieces? So, for example, what was this piece up here?
RAM.
Someone who hasn't talked before. Memory. So this is our RAM, random access memory, okay, your essential storage. And what do we put up in memory? What's always in memory? Data or instruction. So a computer system, nothing magical ever happens. Everything has to be stored somewhere. And so when we have programs that are instructions and those programs use data, which are really the only two things we have to be concerned about in parallelism, right? We have instructions that we want to execute, and we have data that we have to work with. So both are up in a memory somewhere, right? They got to be there and stored there. So you have instructions in there, and you have your data in there. What's this big box down here?
CPU.
CPU. Okay, that's your central processing unit. You can see the CPU has some multiple components that we talked about. Some of the components over here are what?
The GPU.
The register, yeah, in general. So these are also storage. So we have storage here of instructions and data. When we bring it into CPU, we still have to store them somewhere. So these are really registers that allow us to store instructions in the CPU or data in the CPU and work with it. That's really what's over here now. We broke that down into some of the different types of registers. Some of the registers, like this one, allows us to put in there the address of the memory we want to work with. So that was an MAR. This is the data that we want to go back and forth to memory. Some are the addresses of where we're working in memory. Some's the instruction itself. Some are general purpose registers. But the bottom line is these are just the memory locations in the CPU where we're going to store instructions and where we're going to store data. Okay? All right. What are these arrow things?
Data bus.
Those are the buses, bus systems. So the idea is we have to tell memory what address do we want to work with. So we have an address bus, which is just, what, a set of wires, right? So that was the real quick. It's just a way that we can transfer the address we want to work with up to memory so it knows what we want to work with. Here are some wires that work with data. So that's more of a memory data, or excuse me, data bus. Goes both ways. So we can either read from memory into the CPU, which means move a copy of it from memory down to the CPU, or we can write it back. And then we have also our control bus. Are we reading, are we writing? So what are we doing, right? So the CPU has to tell memory what's the address I want to work with, what's the data we're working with, are we reading, are we writing? So it's just a way to get the instructions back and forth, okay? And then we have the key ones over here. So what was the red one first?
The ALU.
Okay, that's the ALU, and what's that doing?
Arithmetic and logic.
Okay, so the A is arithmetic, L is logic. So if you have an instruction and you're going to add, subtract, multiply, divide, if you're going to compare what's greater than, less than, things such as that, that actually happens down here, okay? And then what is this unit doing right here? This is kind of the key beast.
Control unit.
That's the control unit. And what's the control unit doing?
Performs the fetch, execute.
There you go. That's the key to all this, by the way. This thing called the fetch execute cycle. Okay? So this whole thing is performing fetch execute cycle. This cycle happens millions of times per second. And what's actually happening is you're fetching an instruction from memory and bringing it into the CPU. That's the fetch part. The execute part says depending on what that instruction is, you're executing it. If it requires an addition, you're doing it over here and adding. And you're doing that in the ALU. But that's all that's happening. Fetch and execute, fetch and execute. And this beast right here, the control unit, that's what's in charge of that. Okay? So it's sending out hardware signals that's actually doing software for you. So at this level, hardware and software are the same thing. Okay? My software is really a series of hardware signals being sent out. So one software instruction is really a series of these hardware signals. Okay. So there's a whirlwind summary. But where is then the sequential nature of this? Okay? Because we can't do parallel. Okay? And the reason is, what if I want to fetch a second instruction and execute it? Well, what's the problem with that if I would try to do that in parallel?
You just have one control unit.
Yeah, I just have one control unit, right? So in today's modern ideas, the idea here is that this is like one core, okay? And inside the core, I can just do one thing. And so in this case, I can only be fetching or executing, because I can only send out one series of control signals each clock cycle here. And I have the bus systems, or limitation. I only have a single bus system, both internal, that's what this thing is, by the way, and one internal bus that everything's connected to, so I can't put two things on the bus at once. And because if I did, they would conflict. Right? So this is not set up for parallelism, because one, I can't transfer more than one thing around here at a time, or between memory and here at a time. Two, I only have a control unit that's set up to do one fetch and execute cycle. So I can't, I don't have one thing given the instructions. So this is where that limitation is. But we can build on top of this. Okay? Because if we understand this, at least conceptually, we can start seeing how we can move to parallelism and what kind of hardware architecture, at least at this point, we would need for that. And we'll be getting into that a little later. So this is where we're starting. Non-parallel computing, a little understanding that we do have our RAM, we do have our CPU. Okay? The key idea is we have this fetch execute cycle where we're fetching an instruction. And then when we execute, we might be executing in the ALU. Sometimes the execute requires another fetch. This time I'm getting data out of memory. But again, I can only do one thing at a time. And that's the idea behind this. Okay. So, quick summary. So, non-parallel computing, this was just what it looked like. Again, this was an image that came from that lab. But basically, we take any problem, and what we do with the problem is we break it into specific step-by-step, right, that we can solve the problem. That would be known as basically our algorithm, but that's our instructions. And in this case, you only have a single processor, and it can only execute one instruction at a time, or working on one instruction at any time sliced. So pretty straightforward picture showing the sequential nature when you're in a non-parallel environment. You can only be executing one instruction at a time on the processor. Versus, okay, when we get to parallel computing, the idea would be we can be executing more than one instruction at a time. Right? That's the idea that this is showing. And there's different ways to get to that. This one is showing that we have 4 different processors, right? Each one is working on a separate part of the problem. So if we can take the problem and we can break it into 4 different sections. Now, what are some key characteristics of those 4 pieces, by the way, in order to do it never mind, I just gave it. Concurrently, yeah, there's the word that I was looking for. Sorry. In order to be able to execute it parallel, what is the framework of the problem? Well, you have to have concurrent pieces. And so the idea is I should be able to break this problem into pieces that are independent of one another, meaning I can execute piece A concurrently with piece B. If I can do that, then I can write a parallel program for it. So one of the things we got into last week was this concept of concurrency versus parallelism. They're related, but there's technically a different definition where concurrency is more of being able to take a problem, break it into independent chunks. That's concurrency, right? So that I could do each chunk concurrent. Parallelism is then being able to take them and actually execute the instructions in parallel on some type of hardware. So now you're into more of a parallel environment. So we talked about that when it came to parallel computing. All right. So we started getting into what is parallel computing. And so then these were some of the key concepts. So being able to break the problem into these discrete parts so that we can solve the parts concurrently. That was one of the key ideas. And then each part we should be able to solve with a series of instructions. So basically each part we could come up with our own algorithm. Right? And so now if I have each part that's a series of instructions and it can be solved concurrently, then I can go ahead and execute them simultaneously on different processors. So now they are truly going in parallel, okay? And so that's the idea. One of the ideas that's very important too, though, is if I have broke them into processors, so I have a processor 0 and a processor 1 and a processor 2, and in my problem I have concurrent part 0, concurrent part 1, concurrent part 2. This one can execute here, this one execute here, this one execute here. But there are times when we got to control the coordination because this is still one problem we're trying to solve overall. We just broke it into concurrent pieces. So at some point, those pieces have to be controlled. There has to be a mechanism to make sure that we are controlling and coordinating the execution of these still. And so that's the idea of this point here, is there is going to be some overall, some overhead related to taking these first, breaking them into the pieces, but we have to know when is one done and the next one's ready to go, for example, right, if you're doing this. And so there is some control and coordination that we'll see that does provide overhead, but like with many things on a computer, it's overhead that is well spent. For example, what's another very classic concept, another thing that's really overhead on a computer? It really doesn't do anything productive for us, but it's a pretty nice thing to have. The operating system, whoever said that, right? So, I mean, your whole operating system is really overhead. When you run Windows or you run OS X or you're running Linux, you're not running your program, right? You're not running your application. But it's overhead because what it does for you is it does help manage memory. It helps manage the process. It helps provide security. So all the instructions that are being executed by the operating system are really overhead. They're not, and by that we're defining overhead as something that's not going toward resources that are not going towards your problem exactly. But they're creating an environment in which you can solve your problem nicely. And same thing here. We're going to have some overhead associated with parallel processing, but assuming that it's pretty efficient overhead, that's not a problem because it creates that environment in which we can do our parallel processing. All right, so that's a little about the what. Okay, this got back into the concept of the what of parallelism versus concurrency. Parallelism is just really more about the composition of a problem, being able to break it into chunks that are independent of one another. And parallelism then means truly being able to execute these concurrent chunks at once. And so one's dealing with execution, one's dealing with composition. That's kind of the two key pieces. If you'd want to, you could go look at a couple, about 4 minutes of this video. It's from an individual at Google who does research talking about the difference between concurrency and parallelism and their relationship. All right. But we're really getting to this picture. So this is kind of the ultimate picture talking about where is parallelism found in today's modern computing systems. This picture really highlights it. So those of you that were here this week or last week, what did this picture tell us? What were we really looking at? What was the key message that came from this one? What's that? Okay, so let's start here. So we have one core. Let's do a single core. Okay, that would be similar to that Von Neumann architecture we just looked at, right? But we said the Von Neumann architecture wasn't parallel. So what can we do to a core to make it be parallel? Oh, either one. Did you have one, Tram?
You can allow it to do pipelining.
Okay, so one kind of idea is you can do pipelining. So on a single core, you can do pipelining so that inside that core, more than one instruction is in a state of being executed. Okay? You're not really trying to improve the amount of time it can be executed in. It's still going to take the same amount of time as one instruction. But you can overlap the execution of instructions in such a way that you're going to see improvement inside a core. So this is our next topic. We'll actually be talking about it starting on Wednesday for the next few days after that. What is pipelining? So when we focus on pipelining, we're really looking at what can we do inside a core. Okay? As a programmer, you're really not going to take advantage of that. That's just more of you to understand what you can do there. Okay? You can also do a thing called multi-threading. We'll talk about that a bit. What are threads inside a core that allow some parallelism to happen? So just on a single core, through pipelining, which is more of a hardware feature, you just have it or you don't, so it's nothing you really affect as a programmer, but it's there, so we're going to talk about it. And that multi-thread capability. What's a thread? And what can you do as a programmer with threads to do some simultaneous execution? but that's on a core. So that's one place where parallelism occurs, is on that core. In the von Neumann that we saw, that wasn't possible. It wasn't set up for pipelining. It wasn't really set up for the threading. Okay, so we're going to look at what does it take for a core to be set up for pipelining and threading. And as I said, we'll start that on Wednesday. Okay, so that's on a single core. Right? All right. So then where's another level of parallelism capable? Someone here? Okay, so having multiple cores. Okay, so now it's like if I have one machine and it has a chip, well, maybe on that chip I can have quad cores. So now I have 4 cores on there. Or maybe I have, just a dual core. It's 2 cores or 3. And they can have multiple cores. You can have, oftentimes in multiples of 2, because that's just the way we like it in binary. Okay. So how would we relate that? We'll take that von Neumann picture, and imagine if I have 2 cores, I just have 2 of them. I have to have a couple control units. Okay, I probably have some, when it comes to pipeline, that's when you have multiple ALUs. But the key would be multiple cores are really talking about multiple control units, being able to fetch and execute more than one instruction at a time. If I want 2 cores, I'd really want at least 2 control units. If I have 4 cores, I want 4 control units on that chip. Okay, that's what that's talking about. Now, there's other things, like these are quad cores, so that's just one box. You can buy a quad core. There's certainly other things that have to exist there, and we'll talk about that. And there's certain decisions that have to be made by engineers. Do I just have one memory shared by all cores? Does each core have its own memory? Right? Or is there a combination of some memory that's shared and some memory that's dedicated to each core? Right? There's questions like that. How do I balance the load on the cores? Right? Meaning, I got to make sure if I got 4 cores, how do I make sure that if I have a program and I can, in parallel, run 4 different processes, that each one gets going to a core, and that those cores ideally are balanced so that one's not running at 100% and one at 0%. I want things on the cores. That's getting into more of the operating system and software side of things, okay, in terms of balancing the cores and such. But in terms of where parallelism is found, that's there. And connecting it back to von Neumann, that's where we actually have another control unit. So in this case, we have basically 4 control units with those cores. Okay? All right, so that's another level of parallelism. So then what's the third level of parallelism we talked about? The cluster. And that's where you have multiple nodes. Okay? Think of each node as an example, because we just discovered that the Raspberry Pis we're going to use in here are Model 3s, and they are quad core. Okay? And so we're going to each have 2 in our groups, so we have 2, okay? Unless we decide for some groups to go together, then we could actually build this cluster. So now you have multiple nodes that you can coordinate that have multiple nodes that have multiple cores, each of which can have pipelining and multiple threads. And so now you start seeing where we have a lot of different parallelism going along that can really help us attack problems that lend themselves to these parallel solutions, okay? Which are many problems that you guys are going to be faced with because you're interested in ones that have some heavy computation when it comes to modeling and simulations and number crunching. Well, that's when you can start really throwing some parallel architectures at them. You don't want to go sequentially, that would take forever, but if we start throwing things, doing things in parallel, that becomes much more beneficial. So this is really, you can kind of compare this to that von Neumann picture. That's really at the heart of that first question, where is parallelism found in modern day machines? It's found those 3 levels. Inside the core, with multiple cores, and with multiple nodes. We're going to get experience with that, because we're going to be on a quad core Pi, and we're going to put a couple of them together into a 2-node cluster. So we'll have 8 cores going for us, and then those cores, because they're using Linux and Linux supports it, can be doing multi-threading and and pipelining for us. All right. So that's at the heart of one of the key things from last week. All right. So then we got into the whys. Why do you want to do this? So you can write that down. There's certainly benefits to parallel processing. Really, at the heart of it is there's people you're paying a lot of money to do research and simulations and such. And if you can save time and money where they're not sitting around waiting for a sequential process to get done, you're saving time and money as an organization. Certainly they're going to be solving problems, and they're going to be having problems that are more complex and larger, and so you want to be able to use parallelism to solve those and provide that concurrency, and then make use of that underlying hardware. So these are just some of those those ideas. Just taking advantage of non-local resources. There's a lot of applications out there. Anyone ever use SETI? Search for extraterrestrial intelligence? I do. Okay, sorry. I like ancient aliens too on the History Channel. But anyhow, it's just an example of where you can have a screensaver. So this SETI, what it does is it downloads all of these radio signals, and there's just a huge database that has to be analyzed. So what they decided to set up was a screensaver, that if your machine goes into screen-saving mode, well then the screensaver kicks in and it just downloads some data from SETI and analyzes it and then sends it back. So it just has this really, this wide range of non-local sources that it's using to do its processing, which is kind of a neat one. And there's can be certainly other applications like that. But that's kind of the idea, is you have all these non-local resources. Some of them are just desktop machines, and others that you can then put together and suddenly have a very powerful parallel system. So just some of the reasons why we use parallelism. All right, where is it found? And this is, I think, a key one too, as we look around here, is that for the most part, that's most machines you're using now has some level of parallelism to them. The key, though, is the software you're using has to be written to take advantage of it. I mean, you can write software, and if it's just compiled into a very sequential mode, even if I have 8 nodes and I have 4 cores per node, and I'm doing some different things on the core, and I don't write my code to take advantage of the parallelism, it won't. It'll still be sequential. And so I won't see that improvement in that. I know some projects, in fact, Ashby was talking about it, was looking at a project where he was looking at maybe some cryptography and using some different libraries that are there from parallelism, and write their code once just in sequential and then write it with parallelism and just look at some comparison of what kind of speed up you have. And there's different ways. You can just look at wall clock and say, okay, how long did this one take? How long did this one take? You can also start looking at some of the CPU resources to see how fast that they might have been using, what percentage they were using the different cores. But the point would be there are parallelism is used throughout many, many different areas and industries and application areas. And that's all that this was really trying to show you, is that pretty much no matter what you're going to get into, there's going to be benefits of using parallel processing. And it goes all the way. You can just see some of the different application areas. Gets into business, government, medical research, scientific research, communications, forecasting, all sorts of different areas. So that's kind of the key thing there. Okay, and this is kind of where we ended on Friday. Okay, so that was this. I know those of you that were here, thank you for putting up with the review. Appreciate it. Reviews never hurt, right? But this is where we're really kind of ended Friday, and we want to begin here, which is this idea of a taxonomy. And so this is Flynn's taxonomy. It's just one of different ways to classify our parallel systems. Okay? And this one is all about, again, the data and the instructions. And so it's really how much data can you work with at a time and how much instructions can you work with at a time. And they talk about these streams. So think of it as one sequential program as like a set of instruction stream, right? And just working through a piece of data. If I can do one piece of data at a time, that would be a data stream. And so what this one is really talking about is you can either work with one single instruction at a time at a clock cycle, okay? And you can work with one piece of data at a clock cycle. That would be a single instruction at a clock cycle, or I could do multiple instructions at a clock cycle. In data, same way. I can either work with a single piece of data at a clock cycle, or I can work with multiple pieces of data at a clock cycle. That's all that this taxonomy really does, and then you look at those 4 possibilities. So on this side, it's really focusing on the instruction. It can either be a single instruction or multiple instruction. On this axis, you're really looking at your data. It can either be a single piece of data or it can be multiple pieces of data per clock cycle. So let's quickly review, for those that weren't here, the idea of a clock cycle. Computers are really based on a clock, and that clock cycles. And that cycle is called the Hertz rate, which is basically a clock cycle. So that's the Hertz rate. Okay. The faster the cycle, the more Hertz. So like cycles per second. So we can get into our millions of cycles per second. Megahertz, we can get into gigahertz, billions of cycles per second. But basically, each cycle is where something can happen inside the machine. Okay. There's time slices where remember how we sent out those instructions as control signals? So like at time 0, the control unit can send out some control signals. At time 1, the control unit can send out some more control signals. At time 2, the control unit can send out more control signals. And on it goes. Well, each of these time slices would be one of these clock cycles. That's basically what we're talking about there. So what we're really saying is that this time cycle here, this one cycle, okay, how much data can I work with? If it's a single stream, then it would be along the single. And how many instructions can I execute? If it's a single instruction, then it's along the single axis. Okay? So that's really what we're talking about when it comes to single instruction, single data. It's really at a clock cycle that we have. Okay? So in the upper left corner, we have a single instruction and single data, meaning at one clock cycle, I can only work with one instruction or one piece of data. Well, that is the classic Von-Neumann architecture. So we're back to the sequential machine that we saw at the very beginning of our slides. Okay? Obviously not very useful in terms of the performance improvements, but that's where we're starting. Okay. So then let's get over, I'm going to kind of quickly gloss over this one. What if I have multiple instructions but a single data stream? That means at one single clock cycle, I have the architecture in place that I can execute multiple instructions, but I only have one piece of data on which those instructions are executing. Okay? That's not used a whole lot. Okay? You can see that it's rare. There might be some particular applications that want to use the same piece of data but maybe look at 3 or 4 different possible uses of that data. So it sticks that one piece of data into 4 different scenarios and then see what the results are. Okay? That would be kind of what's happening there. All within a clock cycle. But again, it's pretty rare, so you don't see it much, so we're not going to spend much time on it. Okay? The one up in the upper right-hand corner, where we have a single instruction, multiple pieces of data. Okay? That actually is common, not in our processors you're going to use, but in some of our co-processors. And namely, one of the key ones is in our graphic processing units, the GPUs. Okay? Because if you think about it, okay, and this is why that is, in graphics processors, let's just think about graphics. Okay? If I'm just looking at, and it's going to really simplify this greatly, if I'm looking at my screen, and I break my screen into pixels, right? Here's the pixels. And in this case, it's going to be 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4, 5. Okay, so 30 pixels on my screen. We know ours are like, 1,000 by 1,000, right? So it gets pretty big. But the point would be, this is just a pixel. And I might want to do some type of processing of that pixel, right? Well, then I have this another pixel beside it, which is a different pixel. So this is a piece of data. This is a different piece of data. But the processing I do on it is the same. So the idea would be, if I have the ability, okay, to have a single instruction stream, meaning this is the same exact code as this, which is the same exact code as this. So the code is the same in all of these. But this code is working with pixel 1, and this code is working with pixel 2, and this is pixel 3, and this is pixel 4. Okay? The idea is I have the same instruction stream. That's why it's a single instruction. Right? It's the same code, just replicated, but it's the exact same instruction code. I'm just using different data. So I have multiple data streams. In this case, it's multiple pixels that I'm working with. Now I'm in a single instruction, multiple data environment. All right? So that's why the graphics processors are considered the SIMD. So that's that one. And then the fourth and the final is the multiple instruction, multiple data. That is one that is very common to most other modern parallel computers. Right? So again, let's just work through each one of these because there's a slide for each. Even I've given you quite most information already. All right. So in the single instruction, only one instruction stream is being acted on by the CPU during any one clock cycle. Only one data stream is being used as input in one clock cycle. This is just simply a single processor with a single core. Okay? So if you look at over here, okay, we have the processing unit. It's getting an instruction from the instruction pool. It's getting a piece of data from the data pool, but it can only get one instruction and one piece of data inside the processor itself. Okay, so it's the Von-Neumann architecture. It's very simple. As we go into the next one, okay, this is the single instruction, multiple data, so this is the one that would be found in your graphics processing units that you would buy your graphics cards. Okay? And the idea is this. In my instruction pool, I just have one instruction happening. So I might have, in this case, I have 4 different processing units. But I have the same instruction as being fetched by each one of them. So in effect, they're running the exact same instruction each time. Okay? But my data pool will be feeding a different piece of data into each one of those. So if my data pool, as an example, are the pixels on a screen, just like we said here, pixel 1, pixel 2, pixel 3, pixel 4, but each unit is really processing the exact same instruction, but on a different piece of data. Now I'm in that single instruction. Keep in mind that instruction is a single instruction. It just happens to be executed on 4 different, in this case, units, but it's still the same instruction because there's just one stream. But I have 4 pieces of data that would all be separate feeding into it in this case. So that is the SIMD. Okay? And again, that's your GPUs, your graphic processor. So this is just a nice picture to kind of envision that. And this is the MISD, okay? And each processing operates on the data independently. So we have separate instruction streams. So from the instruction pool, okay, I'm going to get a separate instruction for this piece of, for this processing unit and a separate one for this. So they'd be basically running 2 different streams of instructions, but I'm going to use the same piece of data on them. Like I said, this is quite rare. Okay, from this perspective, there might be a few examples, and actually one of them is, let's say this data pool is actually an encrypted message. Okay? And actually this is a better example. So if this data pool is like an encrypted message, and each of these streams is a different algorithm for attacking that message, trying to decrypt it. So this might be one processing unit that has part of the instruction pool that is one algorithm for decrypting it. This might be another one trying to crack the code and decrypting it. But I want the same data to be fed into both, right? But I want to try 2 different ways of decrypting it. So now it kind of makes a little sense why you would do that, right? Because I want same data here, but trying a different algorithm, same data here, but trying a different algorithm. Single data, multiple instruction environment. Okay? All right. And then finally, the MIMD, again, just to give you a visual, in parallel computing will look like this, where you have an instruction pool, and in the instruction pool, if you think about this one, this is one stream of instructions being performed on, let's say 4 of them, another stream of instructions being performed on these 4, so I have, in this case, 2 streams of instructions, but I can be feeding multiple data into these units. And so the data that I'm feeding can be pretty much independent. So that's this type of environment that we're entering into. And that we're really going to be focusing on in this class will be more of this MIMD. So every processor can be executing a different instruction stream. Okay. In this one, it kind of shows that these 4 are executing just a single instruction stream, but it doesn't have to be that way. Each one of these could be working on a different instruction stream potentially. And same thing with this. Every processor may be working with different pieces of data. So this is where we get into the multi-cores, where we get into clusters and the grids. Those are all environments that are really the MIMD environments that we're talking about. Okay. Some cases, the MIMD also include the SIMD subcomponents, right? Single instruction, multiple data. Does this one? Yeah. Okay. And that's what we're showing. Like this is a single instruction. Forget this right here. Okay. For now, this is a single instruction, but I have multiple pieces of data. So this piece of it is kind of an SIMD piece. It's just that we have another SIMD piece here too. So this kind of gives you the ultimate flexibility. I could have, for example, I have these 8 processing units. I could have all 8 of them getting a separate. Now I'd have to draw an extra one here, a 4th there, and then a 5th, a 6th, a 7th, and an 8th. So I'd have 8 separate instruction streams. And then I'd have, just like it's showing here, 8 different data streams. You can see I have 1, 2, 3, 4, 5, 6, 7, 8 data streams coming in. But really I only have 2 instruction streams. So if I would want the ultimate flexibility, I would have also 8 instruction streams, each one going to a different processing unit, and then I'd have a completely, the complete amount of flexibility. This one actually, this is kind of an SIMD approach to one subcomponent, and this is another SIMD approach. So there's just some different ways to configure these, and this is just what this is showing, okay, on this one. All right. But we're going to definitely be in this environment, because we're going to have our Raspberry Pis, which are 2 machines. Those 2 machines will have 4 cores each, and so we're going to be able to set them up in some different configurations to do what we want to do. All right. What's next? Ooh, Windows. All right. So one of the things I also saw that I just want to get into your notes, in this, the Livermore lab, we actually had just some definitions of some parallel concepts and terminology. So I thought I would just hand that out. And you can put that in your book, and then you can go back and we'll discuss these. We'll probably start with this on Wednesday. And then we'll go on Wednesday into pipeline. But these are just some ideas and some things to think about. And again, it's related to, of course, parallel processing. So more just some definitions, but like I said, we're only down to the last few minutes. I'm not going to start them right now. So on Wednesday, what we'll do, make sure you have this, put it in your notebook. We'll start with this, take the first half of the class on this. Then we'll get into pipelining and start the pipelining piece. Pipelining, we'll talk about Wednesday for sure, Friday for sure, probably finish that up Monday, and then we'll get into the next one on Monday. So I think that should catch everyone up pretty well. If you have any questions, let me know. Just be updating your notebook. Be thinking about what you might want to do as a project. I'm not going to be asking you for a few weeks still, but like I said, that's the place where you can really kind of customize your interest in this class. So why you're in here, well, there's different reasons people are in here. And even though we're going to learn fundamentals, we're going to all do some cluster building, we're going to do some programming. Ultimately, you might want to have a project that's focused on, well, what can I pull from this? And so be thinking about that, okay? All right. Have a good one. Stay